All right, number 32 asks us to evaluate an integral. What's different about this one? It's a definite integral. So not only if we make a substitution, we'll also have to do what? Change the limits of integration. Okay? Now on this one, we're going to complete the square. Okay? And completing the square is going to help us turn this into an arctangent problem. No, because you can complete the square underneath the square root and turn it into an arcsine or an arcsecant. But there's not a square root. Okay? So, here's the way we need to do this. If that 13 wasn't there, but instead it was a 4, I can factor that. That's a perfect square trinomial. That's a squared plus 2ab plus b squared. I can factor that and get a plus b quantity squared. But it's not a 4, it's a 13. Oops. So, write it like this. Now, I would like to be able to simply add a 4 right there. And I can. But if I add a 4 to the denominator, I got to subtract a 4 as well. So it looks like this. And that's a little tricky, right? It's in the denominator. Don't subtract a 4 from the numerator. You added a 4 to the denominator. You've got to subtract a 4 from the denominator. And you didn't really change the value of the denominator. You just rewrote it. Now, inside that parentheses, we can factor. Inside the second parentheses, we just want to simplify. So, we still have the integral from negative 2 to 2 of 1 over, but instead of writing x squared plus 4x plus 4, we factor that. It's a perfect square trinomial, so its factorization is a plus b quantity squared, in this case x plus 2 quantity squared, plus, and then the 13 minus 4 turns out to be 9. Did I say 13 plus 4? I said minus because I meant minus, right? Okay. Now, I don't care if you do this next step or not. I'm just making sure it looks like that. Okay? All I did was write the 9 as a 3 squared, which I do really kind of recommend. But as far as putting the a squared plus u squared instead of it being u squared plus a squared, with a plus between them, we ought to know that it's okay either way. All right. So we've rewritten it. It looks like the one that becomes the 1 over a times the arctangent of u over a plus c. But in this case, it's a definite integral. We don't have to worry about that. But we still got to be able to work the du out, or we can't integrate this one. So what's u equal? X plus 2. So what does du equal? Dx. So that means we will be able to make a substitution and turn that into, well, that'll be a squared plus u squared. Dx is replaced with du. So that's good, right? We can do that. But we've got to change our limits of integration as well, because we're changing to u. Let's change to u. So if x equals 2, what does u equal? 4. If x equals 2, if I replace that x with the 2, then u equals 2 plus 2, it's 4. And if x equals negative 2, u equals 0. Well, I like the looks of that. So replace Your limits of integration, instead of being from -2 to 2, it's now from 0 to 4 of 1 over 3 squared plus u squared du. And we're in good shape, right? So the integral of the 1 over a squared plus u squared du is 1 over a, 1 over 3, times the arctangent of u over a, u over 3, and instead of plus c, evaluated from 0 to 4. So let's evaluate. We evaluate first with the 4. So 1/3 out in front. Substitute the 4 in for u. That'll be the arctangent of 4/3 minus, and then substitute 0 in for u. Well, 0 over 3 is 0, so that'll be the arctangent of 0. Yeah, I know what that one is. The arctangent of 0 is 0. So I've got 1/3 times the arctangent of 4/3. And at this point, if this is a multiple choice question, you look and see, are my answers like this? Maybe I'm done. Are my answers in decimals? If they are, I'm not done. So make sure that you're in radian. And then I can do, let's see, parentheses, 1/3 times the inverse tangent, because that's arctangent, inverse tangent of 4/3. And so, to the nearest thousandth, that's 0.309. All right? Make sense? Number 34. All right, so you've just seen completing the square, so you may be thinking to yourself, oh, I bet that's what we do again this time. Well, we'll see. So you got a million things to try, right? You can try rewriting it like we just did to complete the square. You can try making it 2x over that denominator minus 5 over that denominator. You can try that. What else can we try? Why would we want to do that? Yeah, they're on the right track. If you let u equal the denominator, du is going to be 2x plus, it's going to be, 2x plus 2 dx, which isn't what the numerator is, but it's just a constant difference. So let's try it. So du is 2x plus 2 dx. And we can make our substitution. So let's be careful here. Let's make this substitution. All right, we've got the integral of, oh, wait a minute. I'm not ready to substitute. Let me show you what happens if you substitute. Maybe I could right now. I didn't on my paper. Maybe I can make it work out. Let's see. All right. That'll be a u, and then the dx gets replaced with 2x plus 2 du. So I would have a 2x plus 2 and 2x minus 5 du. Maybe I could make that work. I didn't though. I did this. Instead of messing around with my du, making it look like what my problem has, I decided to mess around with my problem and make it look like what my du needs to be. I don't think we've ever done that before. So, that 2x minus 5. See the 2x minus 5? Like I did in the previous problem, I added something and subtracted it. This time it's in the numerator. I added a 2 because I wanted it to be 2x plus 2. But if I add 2 to the numerator, I must also subtract 2 from the numerator. That way I don't change the value of the numerator. So, that's what I did. I kept the 2x minus 5, and I added 2 and subtracted 2 from the numerator. Okay. Now, what that allows me to do, let's save just a bit of writing. That's a minus 7, right? Negative 7. Now, see, we're getting to do almost every technique we've ever heard of in one problem. Now, let's separate it out. Let's make it 2x plus 2 over our denominator, then minus 7 over our denominator. You've got to keep the integral sign. You've got to keep the dx. And when you do, it looks like this. So we've got the integral of 2x plus 2 over x squared plus 2x plus 2 dx minus, and then I went ahead and factored out the 7, but really it's minus the integral of 7 over x squared plus 2x plus 2. And I accidentally chopped off the dx. All right. This step makes me happy and sad. Happy because can't I substitute in that first integral and rewrite that as the integral of 1 over u du? Yeah, that's exactly the integral of 1 over u du. But then the other one makes me sad because I still have work to do. But you with me so far? All right, I left you a big hint in the line above where I scribbled everything out. I left a blank. What do I need to add into that blank to make the x squared plus 2x plus something else into a perfect square trinomial? 1. If I add 1 there, got to subtract 1 on the end. And it looks like that. All right. Is there anything stopping me from integrating 1 over u du? Nope. Let's go ahead. I didn't put a plus c. I'll put that at the end. If you want to put a plus c now because you're afraid you'll forget it, go ahead. So we've got the natural log of the absolute value of u minus 7 times the integral of. Now, this trinomial is a perfect square trinomial. What's its factorization? X plus 1 quantity squared. And then 2 minus 1, 1. Not only does it look good, I'm pretty pleased with myself. Are you pleased with yourself? Yeah. All right, that's an arctangent one. Okay, now, I hate to go all solutions manual on you because we've talked about how frustrating it is sometimes to look in the solutions manual and they've done a substitution and they don't tell you what U equals and it's hard to follow. But I also know that eventually I'm going to make a mistake just copying from one line to another. If I'm not, and I try to be careful, and it still happens every now and then. So, can I do that part in my head? Now, technically, I shouldn't use U, right? Because I've already got U in the problem. So let's call it V. What would V equal? X plus 1, right? That way it looks like, like that, okay? So A is 1, so that's a 1 squared, plus, and then V is X plus 1, so that's a V squared. So if V is X plus 1, what's dV? What's the derivative of X plus 1? 1, so dV would be 1 dx, so dV is dx. So can't I just replace that with V and that with dV and integrate it? And if I do, won't I get 1 over 1 arctangent of V, X plus 1 over 1, and then now throw in the plus C? You with me? Now, if that's too much for you to keep in your head, then don't do it in your head. I didn't, and this is how the solutions manual gets away with it, right? I didn't skip any steps. I thought them through. Okay? It does make it hard to follow. Yeah, you can write, you can get rid of the 1 over 1 altogether because negative 7 times 1 is negative 7. Yeah, and the X plus 1 over 1, let's write that as X plus 1. So, the natural log of the absolute value of U, replace U with what it originally equals, X squared plus 2X plus 2. Rewrite the 1 over 1 as a 1, negative 7 times 1, negative 7. X plus 1 over 1 is X plus 1. Don't forget your plus C. And we got it. So, like I told you yesterday, there are so many different techniques that you're going to have to use. We can't do an example of everything. And then you get to combine them, right? You get a U and a V and an arctangent and a natural log. Number 36. We have the integral of 2 over the square root of negative x squared plus 4x dx. So I'm guessing maybe arc sine, maybe arc secant if somehow something ends up being in front of the radical when we make a substitution. Okay? All right, that 2. Can I factor that out? Yeah, I'm going to factor that 2 out, and I'm going to give you a big hint. Now, underneath that square root sign, I'm seeing whether or not I can use that one. Okay? So it's a squared minus u squared. So I've got to turn, since that's where all my variables are, I've got to somehow try to turn that into a u squared. I say I don't gotta. If I'm going to use this formula, I have to. There's no rule that says I have to use this formula, but that's what I'm trying. Okay? So, since it's a squared minus u squared, I need to get a minus u squared, so I factored out a negative, make that negative, and then inside the parentheses, the x squared is positive, and the 4x is now negative. I left a space for the potential a squared, and I left a space to try to turn that into a perfect square trinomial. Okay? So, say it louder. Plus 4. If I put plus 4, that's right. That's actually a negative 4 that I've added into my denominator, well, added into the underneath the square root in my denominator. All right, so if that's actually a negative 4, what do I have to do to balance it out? Regular 4. Some of us call it positive.
So you always keep in mind
Yes. Okay. Y'all with me? Yeah, we're mostly done now. So it looks like this, correct? What's the factorization of x squared minus 4x plus 4? X minus 2, quantity squared. This 4? It's not multiplied.
oh,
Here's what I'm thinking.
oh, that's mine.
Get right. See, that negative times that parentheses means that when it's a negative of a positive 4, that's really a negative 4. So to balance out adding in the negative 4, I just add in a positive 4. Okay? All right. What's A equal? 2. What's U equal? X minus 2. If U equals X minus 2, what's DU equal? 1 dx. So can I do this one in my head? The U, just put X minus 2 where you see a U in your formula. So we've still got the 2 out in front. Then it's the arc sine of U over A. So X minus 2 over 2 plus C. We okay with 36? 38. All right, so in these previous 3 examples, we've gone to great lengths to contort the problem and force it into one of these inverse trig function formulas, right? So that must mean that every problem we're going to do in this section, we can force into one of those 3 formulas. No, it doesn't. If you'd never heard of these formulas and you saw number 38, what would you let U equal? And what would du equal? 2x minus 2, yeah, dx. What do we wish it equaled? Yeah, we wish it was x minus 1 dx, so now I actually wrote in a step of factoring out the 2. You don't have to put that step in if you don't want to. But I get a 1/2 du, and then on the right side I get an x minus 1 times dx. As long as you didn't try to do one of the others, this one's easy. Now, you know you're going to try to make it fit one of the others first. You know you are. And you're going to be frustrated because it won't work. How do you know ahead of time it's not going to work? You don't. All right, finish that one up. See what you get. You able to get it? You still remember how to work ones like this? So, you got that to look forward to. Now that you know how to do really, really complicated integrals, the easy ones are now difficult. So, we got that going for us. Yeah. Yeah, I mean, it's a good thing, right? When the easy ones get impossible. I mean, you might spend 30 minutes on this one and never think to do it this way.
On the next day, like, oh, you know, okay.
Yeah. All right. Page 385, 31 through 38, 53 through 58, 63 through 68, 75 through 78. I should have had 80 something through 88, but I didn't.